Hello, this is Chun-Shu Wei from the Department of Computer Science at National Yangming Jiao Tong University. Here I'd like to share my previous knowledge about EEG-based motion sickness monitoring and how we can accelerate the pace of research using explainable artificial intelligence. Electroencephalogram, or EEG, has been one of the most commonly used neuromonitoring modality for sensing brain dynamics in the real-world context. Uh, that's due to its strengths, including non-invasiveness, low cost, high portability, and high temporal resolution. And EEG recordings are multiple time series signals of the electrical field measured from the scalp that the signals are sourced from the neuroelectrophysiological activity of the neural population in the brain cortex. And the EEG signals are often decomposed into oscillations with different paces. And from slow to rapid oscillations refers to the components of the EEG time series signal at different time frequency from delta, theta, alpha to beta band. And conventional EEG recording requires an EEG cap equipped with electrodes across the scalp and requires a longer time to set up. But recently, lightweight portable EEG wearable devices using dry electrodes have largely increased the convenience of using EEG in the real world. And for more than 20 years, numbers of studies have investigated the brain response related to motion sickness in terms of EEG features. This is a summary table that shows the representative studies using EEG frequency band power to associate with the level of motion sickness. Early studies use different experiment designs that to create vestibular stimulation to induce motion sickness. And later on, visual stimulation has been applied to motion sickness study. And a previous work in our lab, this one, using VR driving simulator with motion platform to provide both visual and vestibular stimulation simultaneously. And all these studies found the association between EEG band power uh, and motion sickness level, and but the association can be found diverse across different brain regions and frequency band. So these are the pictures of the motion VR driving simulator in our lab. And here's our experiment paradigm. So the paradigm conducts a 65 minutes driving scenario that comprises a 10 minutes baseline where the car drove on a straight road in an autonomous driving mode, and following by a 40 minutes of winding road driving to induce motion sickness, and then another 15 minutes of straight road driving for the subject to rest. And during the experiment, we collect the motion sickness level using a sliding bar on a joystick device. This allows subjects to continuously report the motion sickness level based on their status from normal to having severe sickness. And after data analysis, we found the correlation between the motion sickness level and the EEG band power features to be significant in certain frequency bands, and that's centered at the alpha bands around 10 hertz. And the response can be found at different brain regions as shown in this figure. So the EEG correlates of motion sickness are then used as biomarkers for monitoring sickness level. So this is the processing pipeline we proposed to translate EEG signals into motion sickness level. The pre-processing include artifact removal and ICA, that's independent component analysis, to extract relevant EEG features of motion sickness. And then the estimation block takes the time frequency features as input and incorporates dimensional reduction techniques such as principal component analysis, PCA, or genetic feature selection to to eliminate the redundant information in the data. And then there are regression schemes such as linear regression, radial basis function neural network, and support vector regression to estimate the motion sickness level. So here we're showing the examples of motion sickness estimation of two subjects based on their EEG signal. And here we can see the estimation performs well with high correlation coefficients and low root mean square error. So why we need AI to accelerate brain research, such as developing EEG-based motion sickness? The conventional EEG analysis consists of a series of processing techniques. Taking the EEG marker of motion sickness as an example, we can see that traditional feature extraction, like independent component analysis, can extract EEG component related to motion sickness level. And through time frequency analysis, the correlation between alpha, band power, and motion sickness level can be uncovered. And that can be used to develop EEG-based motion sickness monitoring. However, handcrafted feature extraction is time-consuming and limited to prior knowledge of neuroscience. So recently, people have developed explainable neural networks for EEG coding, and that can perform pre-processing and feature extraction automatically. And therefore, it can achieve end-to-end EEG recognition. And with proper model interpretation, we're able to harvest the features learned by the AI model. So we've designed an open source graphic user interface tool for everyone to load your EEG data and train your model. And you can evaluate your model to interpret the relevant features to gain neuroscientific insight. So this is the framework for future EEG analysis we proposed. The open source platform will provide existing model and interpretation techniques so that you can train your model at your local machine, either at your local machine or cloud. It can be locally if you want to keep the security of your data, which is important, especially for clinical data of EEG. And we also suggest running our tool on the cloud for large-scale EEG data modeling. And our tool can be used to develop high-quality EEG biomarkers of motion sickness based on the predictivity of the model. And on the other hand, it can interpret the features for further exploration of brain mechanism. So here I'd like to thank the funding support from National Science and Technology Council and Ministry of Education of Taiwan. And thanks to my group members. And if you'd like to learn more about research, such as EEG analysis using artificial intelligence, as well as brain-computer interfacing, please do not hesitate to send me an email. Thanks for watching.